Hi, I'm Ali. Today I want to talk about another important interview question. This question is called LRU Cache, and it's a bit different from other problems that we have solved till now. In this problem, we have to design a data structure and then implement it. This is among one of the most popular interview questions in lots of great software companies. And it has been asked by companies like Amazon, Google, Microsoft, Bloomberg, and Apple. So in order to solve this problem, let's first read it carefully and understand it. So the problem says, design a data structure that follows the constraints of a least recently used cache. And here are the information about the LRU Cache class. So as you can see, this class contains a constructor which takes the capacity as an input. And it initializes the LRU cache with a positive size of capacity. And in the get method, it takes the key as an input and it returns the value of the key if the key exists, and otherwise it returns -1. So that means that it takes the key, and if the key is not already in the cache, it returns -1. And if it is in the cache, so it returns the value of that key. And also the method put takes two parameters, the key and the value. It updates the value of the key if the key exists. So if we have that key, it updates the value of that. And otherwise, it adds the key value pair to the cache. So if we don't have that key in the cache already, we should add the key value pair to the cache. And if the number of keys exceeds the capacity from this operation, evict the least recently used key. So that means that, for example, consider that our cache capacity is 3 and we already have 3 inputs in our cache. So if this function is called, we have to remove one of those entries from our cache, and that would be the least recently used entry of the cache. On the follow-up section, it asked us to implement the get and put method in O1. When you are reading the question, try to paraphrase the question for yourself. And also check the keywords of the question. For example, in this example, those keywords are O1 time complexity, key value pair, and LRU, which is our eviction policy. Don't forget to double check the discussion points with the interviewer. This shows that you are understanding the problem well and you have a full grasp on the problem. Before I explain the solution of this problem and write the code, let's go through the example that the question gave us in order to understand this problem better and deeper. So as you can see, we are given two arrays. The first array contains the methods of the LRU Cache class, and the second array contains the parameters of those methods. For example, 2 is the capacity, which is the parameter of the LRU Cache constructor, and 1 is the key value that we should put into our cache. And 1 here is the key that we have to return the value of that based on the definition of the get function. So now I want to solve the problem based on the inputs. So as you can see, the size of this cache is 2, or the capacity is 2. So this would be my cache of size 2. Oops, let's erase it and draw it again. So it is my cache with the size of 2. and this section would be my keys. This column is for my keys, and this column is for my values. And the first item that we should put into this cache is 1, 1. But do not forget, we have to write the output, the number that we return. So that would be my output array. And the first method, LRU Cache, does not return anything, so the output would be null. And the second method is put with the values 1, 1. So we have to add the key 1 and value 1 into our cache. And also, as it doesn't return anything, the output would be again null. The next method is put with key and value 2. So we have to add 2 into our cache. And again, as it doesn't return anything, our output is null. The next method that is called is get, and the parameter is 1. So based on the definition, that means that we have to return the value of the key, which is here 1. So we have to return 1 here. And the output would also be 1. The next method is put with 3, 3, with key 3 and value 3. But as you can see, our cache is full now. So we have to remove an item from the cache. And we have to use the least recently used policy. So the least recently used entry is 2, 2, because the 1, 1 entry has just been called with the get method. So we have to remove the 2, 2 entry from the cache. And then put 3, 3 into the cache. And then we have get with key 2. But as you can see here, we do not have any 2. So we should return -1. So the output is -1. Oops, I missed to write the output of the previous call, which was put. So the output of put is null, and the output of get with the key of 2 is -1. The next method that is called is put with key value 4. But as you can see, our cache is full. So we have to remove an item. And we should use the least recently used policy to remove the appropriate item. As you can see, the 3, 3 pair just has been called with the put method. So we have to delete the 1, 1 from the cache. And we put 4, 4 instead of that. And as it's put and it doesn't return anything, so the output is null again. Then we have get 1, and we just removed the get 1 from the cache. So the output will be -1 based on the definition. Then we have get 3. So we have to return the value of this key, which is 3. So the output will be 3. And then we have get 4. So we have to return the value of the key 4. And it's 4. So the output is 4. And yeah, this is finished. So now let's check if we have done it correctly. Yeah, as you can see, the output is the same with the output that we just achieved and wrote. I hope you understood this problem thoroughly. Don't forget to ask clarifying questions when you are reading the question in the interview, because the interviewers want to know that how do you react when you see a problem that might be a hard problem like this one. So we can ask questions about the parameters of the functions, or the return values, or the boundary of them, and things like that. And on the next session, we will talk about how to implement the get output in O1 complexity and how to implement this problem with the appropriate solution. So before we talk about the suitable data structure for this problem, we should consider several important points from the problem. The first one is that the problem says the policy that we use for eviction is least recently used, or LRU. So this is one of the most important things in designing the suitable data structure. And also, we have to consider that the data is in key value format. So our data structure should enable and accept the key value format. And maybe the most important point of this problem is that we should implement get and put in O1 time complexity. So we have to design this data structure in a way that we can implement get and put in O1. So based on these critical points that the question gave us, let's see what data structures can we use in our design. So based on the least recently used, what do we understand? We understand that our data structure should support an order. I mean, our data should have an order in the list. So, for example, our data should be from most recently used items to least recently used, or vice versa. What kind of data structures we can use to have an order or to sort them in a way? Those data structures include heap or maybe lists or maybe even arrays. So this is the first thing that we understand and we should consider in our design. The second one is the key value format. So what do you think when you want to design a data structure that supports the key value format? Maybe the easiest one is to use a map or some hash table. So this is another thing that we should consider. And also O1 time complexity for get and put, which means we have to have the direct reference to the data. Based on that, we understand that we should not traverse the list in order to get an item or put an item in the data structure. Now, let's talk about different data structures that we may can use based on these critical points. The first data structure that we can think of is a mix of a set or a list and a single linked list. So I just write single LL to save some time. So let's see how that works. Consider that these are our key values that we need to put in our cache. And so how can we design the suitable cache, LRU cache, with using these two data structures? So I want to put all of the keys, which are the first elements, in a set or a list. So this would be the items in the list, which are my keys. And what do I want to do is to have a direct reference to a single linked list. Because remember, we need O1 time complexity for get and put, which requires a direct reference. So consider this is my single linked list. I have 3 items. And these are my values, and these are my keys. And I have a direct reference from my keys to the values that are in the linked list, and that would be 10, 11, and 12. So in this way, I'll have a direct reference. And don't forget that this is the structure of the single linked list. Here is the value, and here is the address to the next node. Actually, here the value section is divided into key and value because the data is in key value format. So maybe I should say that this is the structure that we use. So we have key, value, and the address to the next node. So this is our value section, which is divided into key and value. Yeah. So as you can see here, I just built a map, right? A map of integer, a list of integer, to a linked list, which is here a single linked list. So this is the map that we were talking about. And as you can see, this solution seems really well, and it seems that it works well, but it has a little problem. So let's consider that here is the function that is just called get8. So what should we return? We should return the value of this key, which is 11. Okay, but because we are using the LRU policy, so after this method is called, we have to update our linked list. So because this node now is the most recently used node, and we have to move this node at the beginning of the list, of the linked list, right? But the problem is that because of this format that the single linked list has, we cannot change the next pointer on this node. We cannot change it to 12, so it means that we have removed this node from here and put it at the beginning. So what do we need now is to have a reference to the previous node. So that brings us to the double linked list. So let me change the color and show you how it works. So I want to use here the double linked list instead of single linked list, because double linked list format is that here we also have an address to the previous node. So that means that this node has access to the previous node, and also this node has access to the previous node. So when get8 is called, and I want to transfer this node at the beginning, I can simply change the next node, next address of this node, because now I can go to the previous node from this node. So I go here and I just change the next address to the 12 instead of 11. So in this case, this node will point to this node as the next node, and the previous node of 11 would be null, and I move it from the middle to the beginning with the double linked list. And also I can simply update the previous section of this node to 11. So it means that we have simply transferred the 11 at the beginning of the list. So we have just solved this problem with a map of an integer to now a double linked list. And as you can see, we now can get the value from the cache in O1, and we also can put that with O1 with this double linked list. Because whenever I want to put something, for example, I want to put a key value data, a key value entry that the key is 5 and the value is 13. So it is now our most recently used key, or most recently used key value per, I should say. So here with this double linked list, I just add it at the beginning of this list because this is the most recently used. And with those next and previous sections on the double linked list, I can update that easily with O1. So I hope you understood this problem. It's a little bit tricky, but when you understand it, it's very beautiful, and we can solve this problem with that, and we can design the suitable data structure for the LRU cache with a map of an integer to a map of a list of integers to a double linked list. Don't forget to involve the interviewer with your thought process. For example, here you can do this by analyzing different data structures, as I did. This indicates that you are a strong problem solver and also can communicate about the problem with others well. This is one of the most important skills that a software engineer should have, and they are searching for such a person. And in the next part, I will explain the code of this data structure so you can understand this problem easier and better. Now that we understood the problem and the suitable data structure that we want to design, let's look at the code to understand how should we implement this data structure. But before I explain the code, I should say something about the code. We assumed that we have a pseudo head and tail. So we are doing this because we do not want to check for the null when we want to update the linked list. And that also helps us to write a cleaner code. And also pay attention that the linked list that we have here is from most recently used elements to least recently used elements. So that means that the elements that are at the beginning of the list are those that have recently used, and those that are at the end of the linked list are those that have been least recently used. So keep in mind these 2 points because we need them when we want to analyze the code. Now let's see the code. So we have a class called LRU Cache, which is the cache class, and in this class we have just defined a class called dLinkNode, which is our double linked list class. And as you can see, this class contains 4 variables: the key, value, and previous and next. Because as you may remember, this is the structure of the double linked list. So we have key, value, the address to the previous node, and the address to the next node. So this is the visual form of this code. Then we have a method, which is a void method, and it's called addNode, and it takes a node as the parameter, and this just add a new node to our linked list. So in order to explain this code, I want to show you the visual format of this. So the addNode function works in this way. For example, we have this linked list, and this is our pseudo head, and this is our pseudo tail, and we have a node here called next. So when we want to add the node, we add it after the head because we keep the head and tail fixed, so they will never change, this head and tail, because as I told you before, we don't want to check for null things, and we do want to have kind of boundary for our data structure. So when we want to add a new node, which is the most recent node in the list, we will add it after the head. And let's go through the code. So in the code, as you can see, the node previous part would be head. This is the node, and the previous address would be head because the previous node is head, and the next is head dot. Oops, sorry. The next is head dot next, which is this one. So the next node would do this. This node will point to the next node. We have to update both of these nodes, the head and next, because this node is inserted between the two of them. So the previous part of this node would point to the new node that you can see here. Head.next.previous is our new node. So head.next is this node, and the previous part would refer to the new node. And also we have to update the next in the head node. So head.next would be this node, so that means the head will point to this node. And then we have remove node. This is again a void method, and it takes a node as the parameter, and we in this method we want to remove a certain node that we have been given. So let's show you the visual format in order to understand it better. So consider this is the linked list that we have. Actually, this is our head that I just wrote previous to explain the code here. This is our head, and this is our tail. And this is the next node. This is the node that we want to remove it. So what do we do when we want to remove this node? That means that this previous node, which is here head, should point to this node instead of this orange node, and also the next node should refer to the head node, which is called previous here. So in this case we have removed it. So let's see the code. We have defined two variables from the delinked node class called previous and next, and in previous we keep the node.previous, and in next we keep the node.next. So the previous would be this node, as you can see here, and the next is this node. And what do we want to do is that to do something that the previous node, next node would be next. So that means, as I told you, this node should point to this node, and also the next node should refer or point to the previous node instead of this orange node. So we do that by this code, and this is the visual format of this code. And now let's move to head method. So as you can see, this method is also void, and it takes again a node as the parameter. And what do we want here is to move a node to the head. But remember that as we have pseudo head and tail here, we actually add it to the node after our pseudo head. And this we'll use in cases that we update the linked list. For example, if we call a node, for example, we just call get method, any node is called, so that would be our most recent node, and we want to move it to the head of the linked list, because remember, our order is from most recently used to least recently used. So let's see, what do we do in this function? So I've just called remove node that we explain here, and add node. But let's show you the visual format again for better understanding. So consider this is my linked list, and I have just called this node, so this would be my most recently used node, and I have to move it to the head. And be careful, I move it to the after of the pseudo head node that I have here. So I want to move it here. I want to remove it from here and move it here. So what should I do? First, I should remove that node, as I explained here. So I remove it from here and update the previous and next node. and then add node here and update the head and one node here. I mean the previous and next pointers of these two. So this is the work that we are doing with this method. The next method is popTail, and with this method we want to pop the tail of our linked list. And again, as we have a pseudo tail, so we will pop the node before that pseudo tail. Okay, this method type is delinked node, so it returns a node to us, a delinked node to us, and it doesn't take anything as the parameter. We have declared a variable called res. Its type is delinked node, and we put the tail that previous to that because we want to pop the tail, not the pseudo tail, the actual tail, which is here, which is the node before our pseudo tail. So we just keep this node into a variable called res, and then we call it remove node for this node. And in this case, we have popped that from the list, and then we return that because this is the actual tail that we have, and we return it as the tail. Till now, I just wrote the base functions for double linked list, and here we have the map. We have our map from integer to double linked list or delinked node, and this map is our cache, and this cache has a size, capacity, and head and tail also. So let's see. Now let's see the our LRU cache methods. So first, it is the constructor that takes the capacity, the integer capacity, as the input, and in this constructor we put size 0 and capacity to capacity, and then we have head, which is a delinked node, and tail, which is a delinked node, and here we just made the basic, the base of this cache, and here are our head and tail, the pseudo head and pseudo tail. Then we have the get function, and this function is an integer function because it should return the value of the given key, and the parameter is the key. So in this method we just create a node of the delinked node type and get that given key in the method from the cache. So we call that key, so we have access to the value, and we assign it to a node. And then if the node is null, as you remember from the question, we should return -1, and if it's not, we want to move it to the head because this is the node that is just called, so it is our most recently used elements or node, and we have to move it to the head. And also we return the value because we want the value of the key here. And at the end we have the put method, which is a void method, and it takes key and value as the parameters. So first of all, we want to check that if the given key is already existed in the double linked list. So that's why we get that node with the given key to check that. So if that node is null, that means we do not have any node with that key, with that given key in the linked list. We just make a new node and then assign the given key and value to that node. Then we put that node to our cache, to our LRU cache, and we also call the add node to add it on our linked list. Then we increment the size. This size shows the current size of the linked list. So we want to compare the current size with the capacity that the linked list has in order to know that when we should evict the least recently used item from the list or cache. So as you can see here, we just compared the size with the capacity, and if the size is bigger than the capacity, we just pop the tail, which is our least recently used item in the cache, and we remove that tail with the key of that tail, and we also decrease the current size of the cache. And here this else is for this if. So this shows that the given key has already existed in our linked list. So in this case, we have to just update the value of the key. So in this case, we just set the new value of that node, and then we move it to the head, because that item is our most recently used item now, and it should be at the beginning of our list. So I hope you understood this code. Now that we have analyzed code and data structure, let's talk about the time and space complexity. So as we talked before, and as the question asked us, the time complexity of this data structure and this LRU cache for get and put and eviction is O1, and the space complexity is On, because we have to keep all the nodes. For example, consider this is our linked list. We have to keep all the nodes are the linked list in our memory, so the space complexity would be an order of n. Now that we understood the code and the data structure, let's submit our code in LeetCode and see how it works. So let me hit submit. So as you can see, my last submission shows that our code is accepted, and let's see the details of our code in the analysis page. So based on this graph, our runtime beats about 95% of Java submissions, and our memory also beats about 43% of Java submissions. And our code also has passed 18 test cases out of 18, and our runtime was 12 milliseconds, and our memory usage is about 47 megabytes. I hope you found this video helpful. Also, if you like our videos, consider subscribing and sharing it with your friends, so we can help more software engineers to be prepared for their interviews.